Good morning. My name is Professor Orata, or afternoon, depending on where you are. Today, we want to look at compressors and also try to see how we can develop some relationship to compute the work in these compression systems. So let's look at a linear compressor. So basically, this one works also on a piston cylinder model, so that if you have a schematic of it, let's first of all do the schematic of it. Let's have the schematic. So here we have our piston. So this is our piston. Of course, that's the cylinder in which it moves in. Then we have it's our discharge chamber. Discharge chamber. Now we have some regulating valve at that particular point. Let's call that a valve of sorts. And you have a suction end. And you have our discharge end. And of course, we have multiple magnetic instruments here. So let's say we have our coil. We have our coil. So then we have a magnet. So we have stator there, stator. So let's call that stator. We have a coil. This is a magnet. Let's call that a magnet. So we have a resonance spring. Spring. Also a damper. So this is just a schematic of a linear compressor. We know what a compressor is. A compressor is something, it is a machine to take fluid from low pressure region, compress it, and deliver it to high pressure region. We have talked in other lecture on compressors, and so you can also look at that. I encourage you look at that so that you have a more broad approach to some of these things. So we are seeing that we have a suction end, we have a discharge end, we are seeing we have the piston cylinder system here, and we have a system of magnets and magnetic system here which facilitate all this particular process. We have the discharge chamber. So compressors are very useful machines. They are positive displacement compressors, where they of course there's a solid boundary which stops backflow based on the pressure gradients. Now, what you want to look at specifically is how, for example, can we obtain an expression for calculating work in a compression process? But you want to approach it from a machine point of view. Want to approach it from a machine point of view, where we are focusing on this piston cylinder system. That piston cylinder unit is the one we want to focus on. Now, let us go to our machine. We have the cylinder pressure. P, and cylinder volume, V. So let's take an ideal machine case. And let's say that's pressure P1. Let's call that pressure P1. Let's call this pressure P2 for consistency. And let's call this state point A, that's state point B, state point C, state point D. And so we want to look at the behavior of the compressed liquid, but building up from our expressions from the machine cycles. Let us look at how we will modify that, and to look at that from that perspective. Now, we know that when we take the example of the machine, we still have an outlet and an inlet valve. Remember? Still have an outlet and an inlet. Inlet valve, outlet. And then of course we had our spark plug or fuel injector. And then we have here our piston. Remember, we have our piston. We are assuming those are rings, compression oil rings. These are compression rings. Let's call them compression oil rings. And of course we have a rod. And we are saying that we have this system here. Let's call this our bottom dead center. Let's call that our top dead center. And of course we have our clearance volume. And this rotary motion, and this is a reciprocating motion. Now, we want to focus, because we want to focus about that liquid which is compressed. That compressed liquid. We want to focus on it by working on half portion of this unit, of that pressure volume profile of this indicator diagram. Because remember here, we had said we have this liquid in the clearance volume. Here we have the other leak fluid, and here we have from delta MC. Just look at our lecture on machine cycles. And here we have delta MF exits the system. And here we have delta MC, the liquid in the compressed, in the clearance volume. And so we know that in terms of opening of valves, remember in our linear compressor, we also have seen we have valve which opens into the discharge chamber. Now, we want to use this portion of the machine cycle which deals with compression of the liquid in the clearance volume. And see what is the kind of work expression which you get. So think of it this way. We are focusing on the compression volume because we have the compressor which takes the liquid. It's a machine, takes the liquid from low pressure, compresses it, and delivers it to the high pressure region. So let us just, out of this machine cycle, let us concentrate on this portion on which deals with compression. This portion which deals with compression. That's the portion you want to look at. This portion here. Forget about this other half of that cycle. Now, we know that the volume at state points, at state point A, the volume at state point A, the specific volume at state point A, remember, is delta MF times V1, pressure P1. And the volume at state point D, the volume at state point D is delta MF V2, delta MF V2 at state point D. That's at state point A, state point D. It's delta MC, state point D. Now, remember that for the machine, for this particular machine, when we took work, the cyclic integral of this work here, the cyclic integral of the work here is given by the following integrals for the processes. Following integrals for the processes. That is PdV from A to B plus cyclic integral of the second process, which is actually, we are assuming is a polytropic process. Polytropic, so PVN is a constant. So to use the polytropic equation, we use the polytropic equation here. We use the polytropic equation here, which is for this quantity here, it is 1 over n, 1 minus n into P2 V2 minus P1 V1. And then for the point, that's B to C. Then for the point C to D, C to D, we have P dV. And for the point D to A, which is our center of focus, the one we have isolated, to look at the behavior of this fluid, which is involved in a cycle of expansion, compression, but you want to isolate its compression component. So that is again from D to A, that is 1 over 1 minus n. We are talking about P2 V2 minus P1 V1. Now let's work with the quantities. Now let's work with our quantities. We have defined the state points. So like we said, at this particular point, that's a mass transfer process. That's mass transfer. And so there's no work done. And similarly here is mass transfer. So we have no work done. These are the steps involving mass transfer. We don't want to focus on this particular one. Both of these are polytropic processes. This compression and this adiabatic expansion and adiabatic compression. They are both polytropic processes. But you want to isolate the compression component. Want to isolate the compression component. So compartmentalize this machine cycle in your mind so that you simply focus on this. Forget about what happens, the expansion there. So if you look at our expressions here, so we have said B to A, that is mass transfer, and C to D is also mass transfer. It's also mass transfer. Let's see how this pen behaves. Mass transfer. As you can see. So we have, that is mass transfer. So let us focus on these two. And the one we want to focus on is the one from D to A. That is from state point D to A. That compression process. So let's focus on that compression process here. That compression is the one we want to focus on. From compression process. Let's look at it now. So if we put in the values, we have our value there, W, focusing on the compression process, focusing only on compression. Only on compression. Then we see that W is equals to compression process from D to A. We see that W is equals to the integral. We have already sorted out for this integral. That we have for this particular W. So W is actually 1 over 1 minus n to P2 V2 minus P1 V1. This expression here, we derived it. We derived it, remember, dW. Just in case you don't remember, well, remember we said look at those earlier lectures, we said that dW is equals to minus P dV. And so what is P? For a polytropic process, P1 V1, N is equals to P2 V2, N which is equals to PVN. So we have P is equals to P1 V1N over Vn V2 power N. So dW, if we integrate this particular quantity, dW will be P1 V1N integral V to the minus N dV. And what is that integral? If we use the identity, the integral calculus identity, which we said x to the power n integrated will be xn plus 1 over n plus 1 plus c. If we have no limits, we say that's integration constants, just in quick passing. So we see that the integral of dW in this particular case will be P1 V1 n into V to the minus n plus 1 over minus n plus 1. And so this quantity is here, so that we are all together. So this quantity here tells us that W, this quantity here tells us that W is P1 V1n into V2 1 minus n over 1 minus n minus P1 V1n V1 1 minus n over 1 minus n. Now we know that P1 V1n is equals to P2 V2n. So we can factor that in there. So that W is P2n P2 V2n into V2 1 minus n over 1 minus n minus P1 V1n V1 V1 minus n over 1 minus n. And so clearly you see, if you add these indices, we just use the identity, a times 8 power n is am plus n. That's just an identity we use there. Then we see that W will be P2 into, that is n plus 1 minus n, that will be V2 over 1 minus n minus P1 V1 over 1 minus n. I suggest that you go and look at those lectures which you did in machine cycles. It will help you expound better. Just move very, very fast to make sure that if this is the only lecture you are seeing related to this, you are not lost, so that you know where we came up with that expression for W. Now, all said and done, now let us put in the values for the volume at the state points, so that when we focus on the compression only, focusing on this compression only, then you see the W, let's say the W compression, let's put a suffix there to put more weight on the fact that we're only dealing with that adiabatic compression there. So we will have 1 over 1 minus n into P2, and what do we have? Did we have as volume 2? As volume 2, we had delta MC V2 minus 1 over 1 minus n into P1. And what did we have as volume of 1? In the state point classifications we had there, we had delta MC V1. So if we factorize out these expressions here, so we have W compression. I repeat, we have only focused on this compression process. So what we want to isolate it from the machine, remove, compartmentalize this whole activity. Just focus on that portion. That's why we have put specifically W compression. So that W compression is equals to 1 over 1 minus n, and we have delta MC because it is common in both. We We can pull it out. So we have P2 V2 minus P1 V1 minus P1 V1. Now, if we assume that this fluid behaves ideally, assume fluid behaves ideally. That is, to base PV is equals to nRT. So then we can, if we say that, then we can say that W compression is the same as delta MC over 1 minus N into RT2 minus RT1. RT2 minus RT1. So we can factorize out that so that you have the MCR over 1 minus N is equals to T2 minus T1. W compression. And so, we look at this, the complication which normally occurs with this. Suppose N was 0. If N is 0, remember PV N is equals to constant. So if N is 0, then pressure is constant. If N is 1, suppose we say N is 1. If N is equals to 1, then PV is equals to a constant. This will be closer to the ideal behavior. But that is not very practical. That's not very practical, because if you have the denominator there as 0, then you know mathematically what happens. So in general, we are assuming, we can say for this kind of expression here, we can say that N must be less than 1. So let's define that a compression index. We can say that N must be less than 1 and must be greater or equal to 0. So that we define that compression, that polytropic index. So we must say a caveat. This is a caveat on the polytropic index. So this shows you that you as a specialist in thermodynamics, you must be able to rationalize some of the quantities which you get. You must be able to rationalize some of the quantities which you get, so that for you to correctly use some of these expressions, we have put the boundary that the polytropic index must be less than 1 and must be greater or equal to 0. If we put it as equal to 0, then it will be delta MC R T2 T1. That's the behavior of this liquid, which is in this particular process of compression. So we have isolated this part dealing with compression to try to get a work expression for compression in that particular system using the polytropic equation, where we have compartmentalized this machine circle in and focused only on the compression component. So thank you, and we are continuing with our lectures in thermodynamics.